What is good? What's going on well? It's Friday? Okay, yeah, that's something. I've been a little bit overwhelmed with things, and I apologize. There are some of your messages I haven't gotten to. I think there's only maybe one technical question about pins a pin thing I haven't gotten to, but I know there's some questions about attendance and various things. So Proj believes we've worked out the seating situation, okay? But if there are still issues with seating, send both of us a message and we'll get things resolved, okay? When we say seating situation, we're talking about the exam on Tuesday, okay? Any questions on that, about what's going to happen? Okay, I think we've talked enough about it quite a few times. One sheet of notes, front and back, 8.5 by 11 inches, or A4. Handwritten, must be handwritten, and we should be good to go. All right, feel free to write anything you like on your sheet of notes. In terms of what we're going to cover today, we'll do a little recap, and actually I'm hoping to do, if it works, I kind of have this gutsy desire to do one more finite element analysis example, but I haven't actually done it, so we're going to do it together. But that will be based on normal loading. And then I'll just have a couple sheets which you can see on the, well actually just more like one slide with a little bit extra for some formulas that you might find useful for normal loading problems. And then we'll get into torsion on a shaft. And we'll talk about shear strain, which we haven't talked about much. And we should cap it off with the torsion formula to calculate shear stress. Okay. As many of you know, the content after normal loading today, you don't have to worry about it for Tuesday. Okay. And the assignment that becomes live, or has already been live, but the assignment on the torsion work will be due on Thursday, so after the exam. Okay. All right. We also know that there are some folks who have a desire to go to the career fair, or one of the career fairs that is here on campus. So we'll go ahead. I'll do it at the end, so if you miss it, don't worry. But let me see what I just did. Hold on. I'll show you the slide that you can use. All right, so there you go. If you've got to have an interview or a special social interaction, I completely respect that. All right. How's it going? If you look like you might be going to the career fair.
Thank you.
Already went? Okay, sure. Okay, you already went, so you're here. All right, great. Well, I'm glad you're here. Yes, Mark.
Are you going to get it back? Like, are we going to see?
Oh yeah, you're gonna get it back for sure.
Okay.
It'll be graded, and there will be partial credit.
Is there like a grade scope that you post?
Grade scope. We have the people grading it make marks on the exam.
Grades, you know grade scope?
I do, but we're going to do it with marks on the exam. Okay.
Okay.
And it'll be fair. And if you have issues, you can contest. We have I don't know if it's already posted, but if you have issues with the grading, you can upload your scanned exam to Canvas, and we will allow it until the taking of the next exam. So if you have issues, we'll get the exam back to you. It'll take us a little time, but we'll get the exam back to you. After that, you can review it against the solutions. If you have issues with the grading, then you can upload it to Canvas by the beginning of the next exam, and we'll get back to you. All right. What I would like people to do for that, I mean, you're kind of jumping ahead, but you essentially make a cover sheet and you explain why you believe you should have more credit than what you received. Okay. But we don't have usually that many cases. We try to be diplomatic about things. So thank you for asking. Okay, let's go back to the work. And let me get out of this. It's confusing for me when I've got two screens going here. Excellence. So, last time we discussed distributed axial loading, and we did a couple examples, right? We did the example where you have the bar hanging under gravity, and we also did an example where you have a bar spinning as part of a windmill or some type of turbine. We also have discussed thermal strain and stress, and we introduced finite element analysis. So what I was thinking we could try to do together at the beginning of this class, because I think we'll have some time, is to do another problem using finite element, but I need your help because I actually haven't calculated the numbers yet. Okay, so this is a little bit bold, but I've been a little bit concerned with other things and haven't had as much time to prepare as I would have liked. So what you have here is a bar that is between two walls. Okay, it's constrained. And we're going to give it a linear coefficient of thermal expansion, alpha. We're going to give it an E, an elastic modulus. We're going to give it a length. Okay, and we're going to give it a change in temperature. Okay, so the dimensions, I guess, are kind of nice. 10 centimeters and then 1 centimeter by 1 centimeter for the area. And the change in temperature is going to be 100 K. The material in question looks a lot like steel, okay, with an elastic modulus of 210 gigapascals and a linear coefficient of thermal expansion of 11 times 10 to the minus 6 per Kelvin. Okay. So let's do it together. Let's pretend that this is question 1 on the exam on Monday. All right. How would you approach this? What's that?
What are we looking for?
I'm sorry, Jalami? I'm looking for an approach. How do you approach it? What's that? Oh, what are we trying to solve for? Good question. Solve for axial stress along the beam. Thank you. I'm glad I'm not. So that's a good question to start with. All right. So what do we do? Yes, Mark.
Start unconstrained.
Yeah. So that's probably a good idea, right? Let's go ahead and figure out what the unconstrained displacement. Okay. I think displacement's probably a little bit easier to think about because then we can think about forces. And the equation for that is alpha delta t times the initial length. Okay. Can anyone calculate that out in their calculator, please? All right. So we've got an alpha of 11 times 10 to the minus 6 per Kelvin. We have 100 Kelvin, and we have 10 centimeters. Or you can use Google, but let's try it out. Okay. So keep working on that. What would be another step? And you don't necessarily have to calculate it now. We could wait a little bit on the variables, but I think it's just good to know what that, since we're doing it together, how much is it really? Okay. Yeah. Huh? Okay, so we got to think about the forces involved, right? So this would be under the constitutive category, right? Okay. So now, Jalami, you're saying let's look at equilibrium, right? And what do we know? It's some force, right? And it's going to be the same on either side, right? There's nothing being applied along this member, and we're assuming that it has the same cross-sectional area. But even if it didn't have the same cross-sectional area, or it didn't have the same elastic modulus, we would be confident in saying the force is going to be the same on either side. Okay, and the force inside is going to be the same as well. But if I'm interested, so this is the unconstrained, right? So what we've done here is we've said, okay, we're doing the unconstrained displacement, right? And so it's going out a little bit, and we're saying that this is our delta t, right? And so now we're going to say, oh, I got to apply a force, right, that compensates, that overcomes that delta t, right? And what is the equation that we use for that? That relates a force on a axially loaded bar to get displacement. Huh? Okay, so yeah, we can use force is equal to k delta. That's fine. Okay, I'm going to say delta F just to distinguish here. And
I have a question.
yes.
It's about delta F. So if the forces are going to be like the same and it's constrained on both sides,
Yes.
would there really be a strain due to the force?
Very good question. Okay, so you could think of it, if you wanted, as a compressive strain due to force, but you're right in that there's going to be no strain on this problem, right? So another approach would be to say, okay, what's the stress? I know the E, right? And I could figure out the strain that would have been, and then I look at the strain that's not there. So yes, you're right in saying that. Okay. All right. So in the end, yes, we're going to have no strain. I think it's easier to think of it as having no displacement, but that's another approach. Very well put. Okay. So another way, right, that I think about things is by using Fleet. Right? So this is one of those constitutive relationships that we've established in the class. And I guess maybe I could, I don't even know if it's whoops. This actually probably belongs more on the constitutive. Both of these are constitutive equations over here. Okay. So anyone actually calculate out what the delta t is in the unconstrained? Did anyone get a number? Yeah?
0.4.
Okay, point. Okay. That seems a little high to me.
It's 0.00081.
Yeah, all right. Why did I say it seems high to me?
That's
Because that's what the math says? Yeah, right. So the units, right, we have 10 centimeters, right? So that's going to give us 0.1 meters, right? And we have 100, right? So that 100K, right, 100 Kelvin. So that kind of says, okay, that's only 10, and I've got 10 times 10 times 10 to the minus 6, or 11, right? So yeah, so I would expect it to be, like you're saying, like 1.1 times 10 to the minus 4. That's what you were saying, right? Okay. And that's in meters, like that. Okay, so that's not so much, right? That's a pretty small amount. Okay, so then let's go ahead though and look at what we have here. We have this delta F, right, is equal to FL over EA. Another way to write this is that delta F is equal to, look, F over A, that would be the sigma axial, right, times L over E. Okay, that's maybe a little unconventional in terms of something to write, but nonetheless, we can do that. So since we've calculated out our delta T, and I guess we need to say that, delta F, so this is where geometry comes into play. we're saying that delta T is equal to delta F. And, you know, we're being a little loose here, right? Because when I say loose, I'm saying, well, I kind of have a positive force, but the way I've drawn it, it's not bad because it's going into the bar, right? But this is a compressive force that's acting against the thermal expansion. Okay. So anyway, so if we can rewrite this as saying that the sigma axial is going to be this delta T times E over L. And if you calculate that, who's calculated that one out?
Oh, it's 231 megapascals.
Great. That's a lot of stress, actually. Okay, but good. I'm glad it was in the ballpark of reality. Okay, so this is a steel material, and it's very common for steels to have yield strength greater than a couple hundred megapascals, all the way up to maybe 1,000, but like 800 would be really high for a steel. 700 would be really high for a steel. Okay, so so we're kind of this is good. This is a good physical setup. So let's see how we do this in pre-POMAX and in FreeCAD. So for that, I'll just open up FreeCAD. And how did it go with pre-POMAX? What are your thoughts on it in FreeCAD? Okay. Was it kind of interesting? Maybe a little bit? Maybe you're like, oh, I really wish I was doing this in SolidWorks. I understand that sentiment. Okay. But we'll go ahead. We'll move forward, all right? Boldly. So we're going to get our part here in FreeCAD. We're going to have a cube. And let's see, we're going to have a length, we said, of 10 centimeters and 1 centimeter by 1 centimeter. So we'll go ahead and put 100 here. I think that's it. I think that should do it for us. Okay. Yeah, just like that. Okay, so there's our bar. And we'll go ahead, not export a PDF, but we'll export. And we'll call this a thermal bar. Oh, I had it. Oh, cool. That's right, because I did try. I haven't done this exact one, but I was playing with that. That's why I know. Okay, so we have a thermal bar. And, whoops, not that. But we need to go to the downloads. Okay. And we jump in this. We open pre-POMAX. And we'll go ahead and create a new model. And we'll go ahead and import our, thermal bar, like that. And if things are as we had last time, it's 1,000 times bigger than it should be. Is that right? Yeah, I think that's probably pretty close. Okay, so to what we have, so let's go to geometry, transform scale, and we're going to go 0.01, 0.001. Okay, we're going to apply. Then we're going to go to view, zoom to fit. All right, and that looks reasonable. If we zoom in or zoom out, okay. Yeah, that looks like it could be 1 meter, or 0.1 meter, sorry. Okay, so now what do we do? Well, this problem is a little bit different than the one we did before, in that we had to constrain both sides. But before we can even get to that, we need to create the mesh, and we're going to take the part, and we're going to, let's say, we'll go down to 2 millimeters. And we'll go ahead and mesh. Okay, that looks pretty good. That's a reasonably sized mesh. Okay. So here, I'm going to try not to put any reference points or surfaces in. I will put a material in. We're going to put in elastic property of 210. And we didn't need this when we solved it. We didn't need a Poisson's ratio, but it's probably a good idea to put one in here. And we'll go ahead and we'll also put in some thermal expansion, okay? And the thermal expansion coefficient we said was 11 times 1e to the minus 6, okay?
That was per Kelvin, right?
So it doesn't really matter if it's Kelvin or Celsius. Did you say that? Who said that? You said that? Yeah. Why does it not matter? Yeah, the change is going to be the same, right? They're just offset by 273.15 or something like that. Okay. So yeah. Okay, but what did I something that didn't like this? Maybe I had to do 11e to the minus 6. Yeah. Okay, that's what I didn't like. I don't know. What does this do? 0c. Okay, just to make it like simple. Okay. And that's that. Okay, sections, we have to create one for the solid. So we do that. Okay. Constraints, we're going to have boundary conditions, and we're going to have, we will have essentially, yeah, we're going to have boundary conditions, which are like constraints, but this means something else for pre-POMAX. Context, we can skip that. Okay, initial conditions, this is kind of interesting. I think we should create an initial condition, okay, and we're going to set the temperature to 0, okay, initially. Oops, got to select the part, like that, okay. And then now we'll do a step, we're going to create, and we can do well, let's see, actually. We can do, if we want to look at this displacement, okay, we can do this uncoupled temperature step, okay. I'm kind of interested in the static results. Let's see if this will work. If not, I'll have to go back. And I don't remember what I did here, okay. For the defined fields, so the boundary conditions, let's go ahead. We'll create these. We're going to create fixed, okay, here, and here. Oh, does not, let me see if I can do select. Ah, it's that smart. Good. All right. Like that. So they're fixed. There's going to be no load. All right. Except a thermal load, maybe. Does it let me do a thermal load? Nope. Not here. Okay, so that's not that. And then the defined fields. Okay. Let's see if we can create. Temperature. This is what we want. Okay. And we're going to do the magnitude, all right, of 100 degrees Celsius. I'm sorry, I'm not as familiar with this. Okay, yeah, we had to do a part, okay, like that, like that. Okay. So now let's do the analysis. Let's see what happens. Okay. So it's running. Took a few seconds. All right, this is looking interesting. Okay, so this material has a Poisson ratio. Okay, and what's happening? Well, it looks like it's having some deformation kind of outward. It's kind of getting fatter, essentially, right? And do we expect that? Well, this is thermal expansion, right? So it's going to be expanding in all directions. Now, let's see. We were bold. What did we say the axial stress was? 231 megapascals? That's what I hear you saying? Mm-hmm. Yeah, 231 megapascals. All right. This is what happens when you try things that you haven't really tested. So I'm going to do a query. I'm going to do it over here. Hey. That's not bad. Okay. What does that say? That says 237 megapascals, or 237. You know, it's minus, right? And yes, it's in compression, so that's good. So it's minus. So we did pretty well here, okay, with kind of a brief shot. Any questions on this? Any thoughts? Is anyone tempted just to use finite element for the rest of the class? I've had some people who have been tempted to try to use some of these numerical, or these pieces of software to do a lot of their problems. Please don't do it. you'll end up spending more time than you have to. Okay, the point of the class is to do things analytically, but introduce us to numerical techniques. Okay, so now on your resume, you can even say, I'm familiar with not just mechanical analysis with finite element or thermal, or I can do mechanical finite element analysis. Now you can do thermal and mechanical finite element analysis. All right, so maybe a little bit of a stretch, but you're familiar with the ideas. Okay, great. So thank you for humoring me. I thought that was kind of fun. All right. We haven't gotten to today's new topic, but here are some of the old as in the last couple of meetings that we've had. Maybe some of these are from before. Actually, this Hooke's law, this goes all the way back to session number 3, I think. Okay, but these are some formulas that I think you would want to have on your sheet. Okay, not all inclusive, all right, but there's some good ones. So Hooke's law. And Hooke's law also, right, has, it has multiple forms. I mean, you can even argue that this is a form of Hooke's law, okay? You can argue for sure that these two are forms of Hooke's law, and you can also argue that this is a form of Hooke's law, all right, but now it has the Poisson ratio in there as well, okay, for strain. But let's just go through these. So F equals K delta, we just did that. Sigma equals E epsilon. Stress in a bar is the axial force divided by area. Okay, strain in a bar, we know this is going to be delta over L naught. Displacement due to internal loading. All right, so this one we became pretty familiar with on the last assignment. And hopefully the idea of calculating the internal force, I think that's probably, that's really the hardest part of that, this type of work. Because you can do I know once you have the integral of a function with of x, with respect to x, you ought to be able to do that integral. And as you've guessed at this point, these are not like complicated integrals, okay? But nonetheless, right, you have to figure out what the internal force is, and that is a little bit confusing, especially when you have a distributed load, right? Just one thing, this, again, this came up from one of your esteemed classmates, all right? And it's also on one of the previous exams. And so one of you is already knowing what I'm going to do here. All right? If I have that distributed force, okay, and let's say that this section is L1 and this section is L2. What is the internal force in the first section? Or actually, let's just put it this way. How do we look at external equilibrium? Let's do that first. Because, right, that's kind of our two-step, right? So if I want to know this force right there, what is it? Yes? Okay, huh?
Isn't it equal to the distributed force on the right side?
Okay, that's a distributed force. What are the units of distributed force? Newton per meter. Okay, so how do I figure out what its contribution is? Yes?
Multiply by the length of the section as well.
That's right, okay? And how, so you jumped right, that's exactly the right answer, right? Simplistically though, right, what does that integral look like? If I'm interested in what is the net force on this, let's just call it F net. Or F taut, maybe it should be better. Let's call it F taut. What would be, okay, so you already told me it's little f times L2, right? But how did you get that? Indirectly. Yes, Mark?
The integral from 0 to L2.
That's right. It's the integral from 0 to L2. Whoops. Oh no, please. Okay, good. Like that, right? That's what that combined effect, that's what that effect is. So if you have a distributed force that's not nice and constant, which this one happens to be, right? You could figure out what that overall force might be if you know what the function little f is. Okay? So yeah, so like was said, this is just going to be FL2, right? And like was also said, this force over here is equal to FL2. I mean, lowercase f L2, right? You know what I'm talking about. Okay. If, though, I need the, so that's the easy one. So if I take a slice here, right? Easy peasy. It's just f. What is more complicated, though? If I take a slice in this guy, right? So if I take a slice, and I wasn't really anticipating doing this, but this is just a thought that came. And since, you know, I think you care more about Tuesday's exam than shear force right now, or shear loading, maybe, just maybe. Okay, we'll call this Fi. Right? And if I say that's x, and it's going, right? What do we have here, right? Well, I would say that Fi is equal to the integral of 0 to x f dx. Okay? So the more, right, the more of that length I'm acting, that distributed force is acting over, the higher the internal force is going to be. And once I get all the way to L2, right, once I get to this point, I've got all that force, right? The internal force, we talked about this, right? The internal force right up to this right edge, you know, right next to it is 0. Because that distributed force, even though it's present, has no length, has no portion of the beam on which it's acting. Right? It just builds up that internal force as I move along. Okay? Any questions on this? So anyway, that's the hard part about this, I think, about doing these equations. The integral is cool. We haven't done a problem where, like, hey, there's a varying cross-sectional area, you know. That would probably be, wouldn't that be kind of not so kind if I said, oh, you know, the area is actually a sine function. Then you had to do the integral of 1 over sine or something like that as a function of x, right? That's less happy. Okay. Anyway, let's yeah, and then this is the pli or the Flee equation. This is the spring constant rate of a bar. We just discussed thermal strain. We discussed volumetric strain, dilatation, right? And you know, it's probably not a bad idea to add here that the E is equal, at least for Q, right? For Q, in many scenarios, right, it's equal to 3 times the linear strain, right? You see that right here, epsilon x plus epsilon y plus epsilon z. Okay. We talked about the bulk modulus. This is kind of it's not, you know, it's kind of like a form of Hooke's law, right? But it's the pressure is equal to minus K, the bulk modulus, times the volumetric strain. Okay, and this is the equation you can use for the bulk modulus. And then we talked about these relationships for the normal stresses using Poisson ratio, right? So there have been, already you did the finite element example where, you know, you're pulling, and as you're pulling the bar apart, you've got contraction in the lateral, right? In this direction, so if I'm pulling this way, I've got contraction in this direction and in this direction while I'm expanding in that direction. Okay, any questions? Any questions about normal loading? Any questions about, you know, what, like, your inquiring minds might want to know? Yes, Brennan.
So we're allowed to use a TI-84, correct?
Sure. It does. TI-84, yeah, that's fine. That's fine. Yes?
I have a question that's on the first slide.
Okay.
So the bar with 2 sets of parameters.
Which one? On the which one are you looking at? Sorry.
The one that's constrained on both sides.
Ah, yeah. Uh-huh.
And that with a center line.
Yes?
You give us, there's a problem with the assembly, you want us to find the displacements.
Yeah, yeah.
Gotta stop that problem.
Okay, so I don't have time to go through that right now, but I did put the video out yesterday on how to do that problem. Okay, so I would suggest that you watch that, and if you still have questions, then let's talk. Right? That is a complicated question, right? And briefly, I think the easiest way to do it is the way that I described in the video, which is look at geometric compatibility. Look at the delta due to thermal expansion. Look at the delta that you would need to overcome that thermal expansion with the force. Okay, because just like we did in the previous question, the force on either side is the same. Okay, because there's no intermediate force being applied to it. And so essentially these two bars are acting in series with each other. And so you can think, all right, I've got an overall delta for this thing. Like I can calculate how much the overall thing unconstrained would be. Okay? And I can calculate an overall force that I have to use with these two bars in series with each other to compensate for. And then I can calculate the force. So I guess briefly what I'd say is you would look at the delta. Do I really want to go here? I'm not going to go here because I'm going to mess it up. All right, but look at the video that I've posted on this. Okay, and I think it'll be more clear on how to approach it. Good. Yep. Let's go on. All right. So after you've had a chance to go through this, hopefully we'll be able to do some of the following things. Okay. One that will be fast, and what we're talking about today primarily are axisymmetric, which just sounds kind of fun and nerdy to say, but really we're just talking about cylinders. We're talking about round shafts. Okay? And so, something that looks like that. Okay? So very poorly drawn. Okay? So, and then we're going to be applying torques to these shafts. And we're going to be twisting them. So one thing that we'll discuss today is that the maximum shear stress and shear strain are going to be at the outer surface of the circular shaft. Okay, so this is a check. Okay. We'll also be able to figure out what the shear strain is a distance away from the center line. So this means that it may not be constant as a function of how far you are from the center. So you have the center line coming along here, and we're going to have a row that describes our distance from that center line. And we're going to be saying, okay, what is the strain involved here? Okay. So we'll be able to figure that out. And we'll also be able to talk about the shear stress at a distance away from the center line of circular shaft, right? That makes sense because if we're talking about shear strain, where's my pen? Yeah, or my pointer. If we're talking about shear strain, we can probably relate shear strain and shear stress to each other through some type of constitutive relationship. Okay, just like we have E equals epsilon. Stress is equal to E epsilon, right? We're going to have a new relationship. And just like we talked about the maximum shear stress at the outer surface of a circular shaft, we will also discuss the maximum shear strain at the outer surface of a circular shaft. Okay, so these are some of the things that you'll be able to take away from this session. Okay, so I don't know what happened here, but let's see if it wants to work again. I don't know. All right. So shear strain has something we discussed very briefly. And I think maybe it was the third, I'm not 100% sure, it might have been the third session, okay? And we kind of introduced this idea of boxes or squares that are going to be experiencing some type of deformation. So in the case of shear strain, what you have is some type of displacement at the top, okay, of this box or this cube, and we have a gamma that we use to describe the angle. Okay, again, a little bit bigger. So there's a gamma and a gamma. All right, and that gamma is in radians and is typically very small. Okay, for our class, you don't see this. If I were better, I would have like a nice piece of rubber or something, where you can actually. No, Jeff Hansen does some nice job with this. He'll take a pool noodle, and he's got it all nicely marked up, and he'll twist the pool noodle, and you can see the effect of the shear strain in that twisted pool noodle. Okay. So here's just a little bit more of a derivation, right? So we have some displacement here, and then the tangent of this angle, right, is going to be, this is the opposite and this is the adjacent. All right, so dy, so delta over dy will give us that value. And we can use a small angle approximation, and it's just delta over dy. And that's what we call the shear strain. And if you have x in this direction and y in this direction, we're going to say that this delta dy is going to be, delta over dy is going to be the gamma xy. We don't, we don't go too much kind of 3D on this, okay? But we're just kind of introducing the idea of what the strain is between two axes. Okay? The shear strain is. Now, remember that we have our relationships for for the for normal stress and normal strain. Okay, and that's just sigma equals E epsilon, right? So this is, we're now talking about analogous, right? So this is analogous. Like that. Okay. And here, we don't use E, we use something called the shear modulus. This is G. All right, so this is the shear modulus. All right, well, it's read in there, but this is, sure, we can say it right here. And that's the shear modulus. Yeah. And that shear modulus allows us to relate the gamma, the shear strain, to the shear stress. And I think most people, I don't know, I can't speak for all mechanicians, but most people would say, oh yeah, we have a pretty good idea how to calculate shear stress, especially after today. You'd be able to like, oh yeah, I can calculate shear stress. And if I had to figure out what at least for these types of analytical problems, if I have to figure out what the shear strain is, I'm first going to calculate the shear stress, and then I'm just going to relate it to the shear strain via the shear modulus. Okay? Because most of these problems, as you'll see, are going to be 2.5D in nature, and we're not going to be dealing with shear strain between X and Y and, say, X and Z, okay? Okay, so then the other thing maybe to point out is that this kind of description is a little bit of a, I don't want to say a lie, but the hardcore mechanicians won't draw it like this. Okay, because now you're saying, oh, I've got this like flat thing that it's constrained on the bottom. What they'll often draw is something that's more like this, where I've got this diamond distorting shape like this. And these angles here, okay, although they're not equal, these angles would be the gamma over 2. All right. So if you look at different texts and things, you're going to see, oh yeah, that's actually more how they think of the shear strain, or the shear strain. Okay. Okay. So, oh yeah, and then we'll derive this later. Okay, but the shear modulus is equal to E over 2 times 1. It's E over 2 times quantity 1 plus nu. And this equation, this will be something that you write on your formula sheet before the next exam. And this one too. Okay. So now we're just going to do kind of some thought experiments, not with a lot of math. All right, initially. Okay. Let's say that we've got some type of circular shaft. And you know what, I'm having trouble. I just want to make sure that this is recording because I let people go. Okay, it seems to be recording. Okay. I think the video is all messed up, but that's okay. At least the audio is good. Let's see here. Yeah, I think the video is all messed. You don't need to see me. That's fine. Okay. So, imagine you have a rod sticking out of a wall. And let's draw a whole bunch of grids on it around the outer surface. Okay? So, I think we talked about this before. When you're trying to figure out, okay, which direction the shear stress or shear strain might be, it's often not bad just to visualize what would be happening if you had a rectangular grid and what would be happening to the boxes or the shapes of those rectangular grids if I were to twist it. So that's what we're doing here. We apply a TZ, and this is a normal. Okay, coming out, so that means that, by right-hand rule, what am I doing? I'm really twisting it like that. Okay, and what do you see? You see that this nice grid with 90-degree angles at the vertices has now become distorted, right? And like this face has moved down or has moved circumferentially a little bit down this way relative to this face. And if we were to draw a line, okay, so you drew a line like across the top, for example, but then you twisted it, okay, what would happen to that line? This is a linear isotropic material, so, and an elastic material. So what you would see is that line would then come down like this. So at the wall where it's fixed, this point, it cannot move. It cannot do anything. It's stuck, right? But as you go farther from it, it's going to have a larger angle of rotation. Okay? So this is kind of one of the first things that we understand. If I have a rod, and it's longer, and everything else is the same as a shorter rod, the angle of displacement will be larger, okay, at the end. What does this remind you of that we've already covered in this class? If I have a material with a given cross-sectional area, and I make it longer,
Axial displacement.
yeah, axial displacement, right? If I have a bar and I apply the same force and I have the same stress across it, the longer that bar is, right, the more the displacement is going to be. The stress can be constant across it, but the displacement is going to increase as I make it longer and longer and longer. Okay? So this is analogous. On Thursday when we get back, we will introduce the equation that describes. I'm sorry, you're not going to get that equation today. All right, that's okay. All right, it's TL over JG. All right, just like we have FL over EA. All right, but anyway, and we'll introduce how you do that. But we're not going to derive that today. But that's the amount of displacement that you would angular displacement you would expect. And obviously, if you're halfway there, you're going to have half the displacement. Okay, so like you see this, the phi at L over 2 is equal to 1/2 the phi at L. Shear strain. Oh, right, and yeah, I forgot. How could I forget? What I want you to begin to imagine is this table as a slice, all right, which represents a whole pizza. Okay, it's a slice in this, in kind of if the rod is going there, right, it's kind of this slice coming right through. So each rod is a stack of pizzas. Okay, and what we're looking at are slices of pizzas, like this, right? This looks like a slice of pizza. Okay, so when we start to think about these angular displacements of pizza along the rod, okay, we cut out a slice of pizza. Okay, yes, this is from The Office, and that is from a well-known Rutgers pizza place on campus, within 5 minutes of here. Okay, so let's talk a little bit about what's happening with one of these pieces of pizza. Okay, a piece of pizza, or I'm sorry, let's talk about the whole pizza. A pizza pie, right, has some thickness to it, right? Okay, so let's imagine, very poorly, okay, that this right here is one pizza, like from, this kind of, from this box, right, represents one pizza, and then we turn it sideways, and now this is a pizza pie, okay? And I haven't twisted anything yet, okay, no twisting, although it might look like I twisted it because my drawing is that bad, okay? I have here drawn, this is like the crust, right, of the pizza, and this is like the innards of the pizza. Okay. And I have at point A, which is on the outside of the crust, and I have E and H, which are where the outer crust ends. I guess, maybe I don't know my pizza well enough. I guess we still consider the underneath part of pizza crust, right? Right? But when kids don't eat their crust, usually you're referring to just the outer rim, right? Okay, anyway. So what's happening here? And then I've got this rho, okay? And I've got the C. C is important, rho is important too. So C is the radius of my pizza pie. And rho is a variable that we use to describe the distance from the middle of the pizza pie to some arbitrary location. That's rho. And the thickness of the pizza is given by delta Z. Right? So now, what happens? Now, we apply some twisting. Okay? We apply a torque. We'll call it TZ. Right? And here's TZ being applied. Okay? Imagine now this is like some cylinder that went to the floor of the room. This is the table. All right? But this table represents one pizza pie, and this is a slice. Right? So, a couple things happen. One, there's all this there are all these pizza stacks underneath the table. Okay? And so, just like we discussed prior, right, there is going to be an angle of twist associated with the distance from the fixed end of my rod. And that displacement, that angular displacement, we can think of as phi of z. Okay, so point D and H, all right, they would have moved over when they have this twisting, this torque applied. They will have moved over to this location. Okay, so D goes to D1, H goes to H1. All right, and that's just because there's all these pizzas stacked below. Then, when we get up to the top of the pizza, what we see here is that there's some kind of interesting behavior. A and E have experienced this same angle of rotation, phi of z. All right, so they move over that, but since they're a little further up, okay, since they're a little further up than this plane that has D and H in it, okay, since from the bottom of the pizza, right, this is the top of the pizza, they also rotate a little bit more, right? Because as we said, length, right, the longer your length, or as you go in length, you're going to have more twist, okay? And in addition, look, there is going to be some additional, so there's going to be, so this like this A naught and E naught, right, is what you have with this with what would be phi of z, and then you rotate a little bit more beyond, okay, what you had at the bottom, okay, and so this is the z direction, all right, and if we then look at things, all right, with the phi, you see this phi direction. This is kind of confusing. R is the radial direction, the same direction as rho, okay, but if we look at the did I say theta? The theta direction, sorry. All right, that's circumferential around. If we look at that, what we can see here is that with this delta z, okay, there's some angle here, and there is going to be a shear strain, okay, between theta and z. Right? Now, what is this angle of rotation? Well, this angle of rotation is going to be the radius times, or sorry, the angle of rotation here is going to be what we call delta phi. All right, that's this right here, or it's in here, in fact, that angle of rotation, right? And the radius times that would give us this arc length. So you see this arc length given by the highlighted, the yellow grayish line. That arc length is rho delta phi, right? That's this arc length right here. And so if I know that arc length and I know how high I went up, that's how we calculate the gamma. Any questions on that? All right. So this is connecting shear strain to twisting of a rod. So now when you look around and you're like, oh, I'm using a screwdriver and I'm applying a torque, and one end is kind of fixed, at least in many cases, relative to the other end, right? I'm actually introducing a shear strain into that screwdriver. And that shear strain can be constant along it, right? But I know that the longer the screwdriver is, the more the twist will be on one side. Okay, so now we take the limit as the delta z goes to 0, and we get a nice differential form for the gamma, which is rho d phi dz. So as the pizza slice gets thinner and thinner and thinner, right, and approximates 0, then we say it's just rho d phi dz. So here's shear strain. Okay. Shear strain is going to be dependent on rho. Okay. Do you see that too? So the further, right, rho is describing this arc length here. But if I were out here at where rho is equal to c, right, where it's equal to the radius of the pizza pie, then this arc length is larger than this arc length, right? This arc length on this green region is longer than this arc length for the highlighted yellow gray region or line or curve. So the shear strain is going to be higher out here than it is here. And as we go inner, right, if rho equals 0, well, the math says that too, the shear strain is 0. So if you're at the center of your screwdriver as it's twisting, it's going to be 0 as well. Okay, for a section with constant internal torque, okay, gamma is independent of z. Okay, so that means that along the length, right, the shear strain doesn't care, and that is very similar to the axial strain we talked about for a bar, right? If I'm applying a force and I'm stretching out this bar, yes, the longer the bar gets, the more displacement I have, but the strain along that bar is the same throughout the bar. And the same thing is true for shear strain. Okay, as at least it's independent of the z, right? It's dependent on the radius on the rho, how far it is from the middle of or from the center line. But as long as it's at the same rho, it's going to be constant along the length of the rod. And the shear strain gamma is a maximum when rho equals c. That's another true statement. Okay, and we already kind of discussed that, right? When rho is inside the annular crust, it's less than when it's on the outside of the annular crust. Okay. Gamma max when rho equals c, gamma equals 0 when rho equals 0. Yes, we said that already. And there's a linear gradient from rho equals 0 to rho equals c. That's true too. So we can say that the gamma at a different radius or a different rho, okay, is proportional to the maximum strain. So if I know what the maximum strain is, which is going to be happening at the outside of the crust, if it's happening out here, right, then I can figure out what the gamma is, you know, on the pepperoni or something, because I know what the distance is from the middle, okay? Or sausage, whatever it is. Yes, I did eat the pizza afterward, after taking the pictures. I justified it. I said this is for purposes of teaching, and I enjoyed the pizza more. Okay. So, angle rotation along a shaft. If we have an angle rotation of 0.1 radians at the end of a shaft, what is 5 L over 2? Well, and they give us that the length is equal to 1 meter, right? So that's the maximum Z. So if we're just halfway along the length, right, it's just going to be half of the shear. The shear strain is going to be the same. The phi, the angle rotation, is going to be half. Okay, because that's what we see here. And what is the shear strain at a distance from the center line? Rho at Z equals L over 2 and Z equals L. Well, it's the same, okay? And, it's the same as Z equals L over 2 and it's the same as Z equals L. But if it's half, right? So this is we're saying that, this is, we can say that the gamma, right, is going to be dependent on the rho, right? So whatever that distance is from the middle, okay, times this this displacement. Okay. Right? What we're saying is rho phi over z essentially. Okay, we can use, because it's a linear gradient, so we can say that we have, if we know what the phi is and we know what the L is, we can figure out what the shear strain is, right? And that should be familiar too, because remember, how did we define regular axial strain as the delta over the length, right? The displacement that we had over the original length. So this is kind of similar, saying, hey, what is the angle of rotation and what is the length? Okay, and times rho, that will give you the shear strain. Okay. Torsion formula. Okay. Now, we have this equation for rho. We have this equation for gamma, and it's equal to rho d phi dz. Okay. And we've said that the maximum shear strain happens at the outside. Okay. So that's at the outside of this cube. And we have that the gamma on the inside of this circular cross section. All right, so as rho goes up, right, we know that the gamma is going to be proportional to where we are. Okay, so if rho is equal to 0, it's 0. If rho is equal to c, right, we have gamma max. We also know that tau equals g gamma, right? This is Hooke's law, but for shear stress and shear strain. So we have this idea now that tau, the shear stress, is also going to follow this relationship. Okay, right? So we could say, oh, I can multiply. I can say, if I multiply g on both sides, right, I can then just say, okay, now I've got a tau, and I have a tau max, right, because tau is equal to g gamma. So this is saying that the shear stress is going to be proportional to the radius, or the rho over the radius, okay, the distance, okay, and we can begin to draw now what a profile of shear stress would look like. So imagine now you've got this face, and there's a bunch of shear stresses, okay, that are building up as you get farther from the center line. Okay, so now, if I want the total torque, okay, torque, right, that's the twisting moment that I'm applying to this. Well, look at this. What is torque? We usually define it as R cross F, right? So R cross F, right? Look, this is rho, but now we have a tiny force acting on a tiny surface. So we integrate that. So this shear stress acting on the dA is like a little dF, okay? And I have rho cross it, but since they're orthogonal, I get rho times it. And if I integrate all these up, I get the torque. So now we can say that the torque is equal to this equation, and we can substitute in this tau here, right? It's going to be rho over c times tau max dA. Rho and, we have c and tau max as constants. We have rho here times rho there, so that becomes rho squared dA. And so now what we do is we define this quantity. The integral of rho squared dA, okay, is what we call the polar moment of area. Okay, and that we define as J. So J is equal to integral of rho squared dA. That plugs in here, so we get tau max times J over C. Okay. And the tau max can be written as torque times C divided by J, right? This is just manipulating. So we have tau max, right? There's torque is TZC over J. And this equation, since we live in New Jersey, this is TC and J. This is TC and J. All right? That's how I remember this one. So if you ever need the shear stress, just go to our friends at the College of New Jersey, and they'll give it to you. we have a max shear stress and we have a tau, right? And the max is just using the outer radius. The tau is going to be using the distance from the center, the rho, and they're both over J. Okay, any questions on this? Yes? The rho is given as a radial distance to an arbitrary location from the center in the material. So we're talking about circular cross sections, right? Just like you see here, it's just a circular cross section. And we are saying that wherever I am relative to that center line, that's the rho. Okay? Does that make sense? We're defining it. And that's how we define it. C has a special definition as it is the radius of the actual object. Right? So C is just the radial distance to the outer surface. Okay, so those are our two basic definitions. Okay, and J is this integral of rho squared dA. Okay, now what is a polar moment of area? Well, one way to think about it is to think about it as kind of this this ratio, right, between torque and shear stress, right? So if you have a high polar moment of area, it's going to make your shear stress low for a given amount of applied torque, right? So you can think, oh, the higher the polar moment of area, the lower the stress I'm probably going to have. And you can then kind of get an idea of, well, if I make my shaft, my rod, larger and larger in diameter, it's going to be stronger and stronger, meaning the amount of shear stress that I'm going to have inside of it is going to be lower and lower and lower. Okay? So we have this idea, J is somehow related to radius. So if I make the radius of a shaft larger and larger, right, it's going to have a lower stress. And it's not just radius, it's actually radius squared. Okay? So if we do this integral out, all right, and it's not that complicated to do it, all right, you can think of a bunch of annular rings, okay, with a width of d rho, okay, and you can think of that being a dA, right, and we're integrating that, okay, from 0 to the radius of the circle, all right, then we have this equation, right, where we have a dA, right, so that becomes 2 pi rho dr, and we have, so the dA is 2 pi rho d rho, sorry, and we have rho squared already there from this, and so we do this integral out, and this is what we get. We get J is equal to pi over 2 c to the 4th. Okay. So it's not just this is kind of a biggie deal, right? If you make, I mean, yes, it's proportional to rho squared in this integral, okay, so that's a true statement. And I was saying if I make the radius larger and larger and larger, right, the stress goes down and down and down, but it's actually, right, this is pi over 2 c to the 4th. This is a c in the numerator, so it actually goes down with the inverse of c cubed. Okay? Because you have this, or even if you have t rho, right, it goes down, right, you still have a radial component and you have a j. And that's something also important to realize, is that in both of these equations, the j is the j for the entire circular cross section. Okay? So if I go to a smaller radius, I don't change my j because I'm at a smaller rho. I still calculate it over the entire circular cross section. Okay. Now shear strain in a twisted shaft. Well, we just use Hooke's law. Hooke's law now is tau is equal to g gamma. So we already established that tau is equal to t rho over j. and the maximum tau is Tc over J. So we can go ahead and we could substitute in the G gamma here, all right? And then we multiply by 1 over G on both sides, and we just get the gamma is T rho over JG. And the maximum shear strain is going to be at C, where we have Tc over JG. So now we've calculated, now we can figure out what the shear stress is in a twisted rod if we know the torque, and we can figure out what the shear strain is as well. We've got a few minutes, good. Do you remember this? This is back when we talked about static equilibrium in session 2. Well, before we can calculate out, at least with the equations that we have here now, right? In order for us to be able to calculate what the shear stress or the shear strain is, we need to be able to know what the torque is, which means that we had to go back into our understanding for equilibrium with rods and shafts. Okay? And so as a reminder, right, we often look at the external equilibrium first. Okay? And we often arbitrarily pick a coordinate system or axis, and we use Newton's second law. And then when we want the internal, right, we have to do a slice, and this is where we usually follow a convention, right? The convention being, when you take that slice, make sure that you're using the right-hand rule when you prescribe the direction of the torque, okay, or the angle of twist, usually, that you're interested in describing, okay? So when we think about the TAB here, right, and so this is the torque in between A and B, I'm going to try to follow my right-hand rule based on not this surface, but on this surface, which is over here. And again, we apply Newton's second law. Okay? And yes, this problem is pretty simple in that we know that the internal torque is going to be equal to the external torque being applied on this side, which is equal to the external torque applied on this side. And if we applied, if we took a slice and we exposed the left side, we still want to make sure that we follow the right-hand rule, and that's still going to be TAB. And notice they're in opposite directions, right? But they're describing the same behavior. And they're going to have the same magnitude, just like that. Okay. Yeah. Any questions on this? Okay. Good. There will be some assignments. What did we cover today? So we did a little bit more finite element analysis. We did one that involved thermal expansion being constrained. And we talked a little bit about formulas for normal loading. And then we went on to talk about torsion in a shaft, defined or redefined or revisited shear strain. And we talked about overall deformation, but we didn't give a quantitative equation for it yet. Talked about shear strain, we'll talk about shear stress. And that torsion formula, that Tc over J, that formula is often what people use, what they refer to as a torsion formula. Okay? Great. I'll go ahead and put up the attendance. If you have any questions.